Hello everybody. In this lecture series I'm going to talk you through how I would apply the chain ladder method in practice to a few example datasets. Reserving is an art, not a science, so it's not a step-by-step set of instructions, but it should be helpful in explaining how I go about selecting link ratios to predict future claim development, including some quick checks to ensure that my historical data is reliable and that the chain ladder method is an appropriate choice. I'll also cover how I would smooth through unreliable link ratios in later development periods, and how to select tail factors, and finally how to check that my predicted ultimates from the chain ladder method are as reliable as possible. In the first video in this series, I'm going to focus on assessing and selecting link ratios in the chain ladder model, as well as some checks you can take to ensure that your historical data is reliable for predicting future claim development. So let's start modelling. In this first example, and it is quite an interesting example, a little bit extreme, but hopefully it'll illustrate some of the things I look at. So I'm going to use an annual origin period, annual development triangle. This is fine for an example, but as discussed, it's highly likely that a real-life application would require more granular data than this. In this example, I'm going to fit a chain ladder model to just one triangle of data, and again, as discussed, it's highly likely that you would need to look at more data triangles than this for a real-life application. And lastly, I'm just going to fit a single chain ladder model, but again, it's highly likely that you would need to fit multiple models to the same data triangle to get comfortable with your selections and to assess the sensitivity of your model to any subjective assumption choices. On an aside, as a reviewer, when I see that someone has fitted just one model to the data, then this tells me that this is an easy class and that the modeller must have known exactly how it would run off. Is that really the message you're trying to convey to the reviewer? Conversely, fitting a variety of models to the same triangle will enable you to try out various hypotheses and also enable you to compare the results from the various calibrations to get an implicit view on how uncertain this class is, which is clearly going to be helpful to both you and the reviewer. I'm going to illustrate everything through a series of exhibits. On screen I'll indicate in the top right how you can reach these same exhibits using one of the most popular reserving tools used in the market. Now I'm not going to say which tool that is, as the tool itself is less important than how well you use it. So you should be able to reproduce all these exhibits in whichever tool you use, or via a side calculation in a spreadsheet. The first exhibit we have is our triangle of link ratios. This is a triangle link ratios covering an average incurred cost of claims for our particular segment which we're modelling. However, if we just focus on the link ratios, then we miss the underlying data, which we know is important information. So let's bring that back now. At this point in our modelling, we should have gone through all of our preparatory steps and have well segmented data covering all the right data elements ready for modelling. However, it's still important to be certain that the data is sufficient and homogeneous, as well as to sniff out where the data may be unreliable. In this example, I can see that broadly the average cost of claims is pretty consistent from accident year to accident year, ranging from around about 20 up to 40 in the first development period. If the data wasn't consistent, and for example I saw some years with a 40k average cost and others with a 4 million average cost, then I might start to question how homogeneous my data really was. But here, it looks okay. And it looks like I can rely on all the historical data at first sight. Next, I want a quick check of whether the link ratios are broadly consistent, or whether they trend down towards 1 as we'd expect, i.e. when all the policies have completed the policy life cycle. This exhibit plots lines representing the link ratios for each origin period. So for example, the grey line shows the link ratio for the 2004 accident year, which has a value of about 1.4 in the second and third columns. In this example, we do get a trending down towards link ratios of 1, meaning all claims have completed their journey through the policy life cycle within our triangle, which is a good sign for the validity of the chain ladder method. However, we can immediately note how inconsistent the link ratios are for the first 4 development periods, so up to 5 years. It's often the case that link ratios are broadly spread, volatile, at first, but it's a little surprising to see such disparity 4 or 5 years into the policy life cycle. So I'm already a little concerned about the homogeneity and reliability of the data here. Next, we'll consider if there are any obvious trends in our link ratios over time. So what we're looking at now is various calculated averages of the historical link ratios, which we might choose to represent our true but unknown development pattern to apply to future development. It's worth reflecting at this point what kind of averages to use. The most common in my experience are volume-weighted averages, whereby the weight given to a link ratio is the development data preceding that link ratio. This is an improvement on simple or unweighted averages, as it gives less weight to smaller data points, which will implicitly be less reliable. I think technically using the square root of the volume as your weight might be more correct, but it's a little overcomplicated and harder to explain, which is why most actuaries stick to simple volume-weighted averages. Similarly, you could introduce a decay factor into the weighting, say giving 90% to the power of 1 to the weight given to the most recent link ratio, then 90% squared to the next most recent, and so on. Again, this does sound like a nice feature to add in, but again does make the calculations a little unwieldy and less easy to explain. Whichever option you do use, it needs to be justifiable and documented in your modelling notes. On the chart, the dark blue line is showing the volume all average of our historical data. So this is taking a weighted average of all the historical link ratios for a given development period, again weighting on the actual development data. Whereas volume 5, the green line, is taking a weighted average of the most recent 5 link ratios in each development period, and so on. It's immediately striking that the volume all and the volume 1 link ratios are very far from all the other link ratio averages we're showing. Now volume 1 is just looking at the latest link ratio in each development period, and so we can ignore that as a sensible candidate, except in some very special cases. Volume 2 to 5 all look very close and consistent, indicating stability in recent periods. Comparing volume all to volume 2 to 5, this suggests that recent development has shifted to a new normal from the older data, which developed markedly differently. I've got red flashing warning lights going off in my head here, and in practice would need to check my notes on discussions with claims and underwriting teams. For example, did we start writing different business 5 years ago? Will the claims team change their approach to claims handling then? Has there been some kind of legislative change? Let's do another test to check the validity of the historical data for rejecting the future claims development. One really good test of your data for validity is to look at residuals. What I mean by residuals is the difference between each actual link ratio and the expected link ratio from the chain ladder model, normalised through an adjustment factor so we can compare across development periods. It's important to do these tests early on before we made any selections, as any adjustments we make to the expected link ratios will naturally bias the residual test. So make sure you're using volume all average of the link ratios and you're not using any curves to smooth through the data before you look at the residual charts. This chart here is showing us the link ratios grouped up into columns by origin year. In this example, accident year. The chart is also showing us the average residual for each origin year, the solid blue line. Some tools will call out exceptionally high average residuals, and in this example, I'm surprised by how low the average residual is, both for the earliest and the most recent accident periods. As per our checks earlier, this is corroborating our view that the older historical data may not be appropriate to apply to future development, as the true underlying development profile may well have changed over time. If we now look at those same residuals, but grouped up into columns by development year, then we can quickly check that there's nothing odd in the development data. As we can see, the average residuals are very well behaved, and there are no exceptional development periods. This is often the case given the development-based calculation of the expected link ratios in the chain ladder method. So now let's look at the most powerful residual chart, the one showing us calendar residuals. This is most powerful as we often see by eye trends going horizontally in our triangle through development periods or vertically in our triangle through origin periods, but it's much harder to spot diagonal effects through calendar periods. So we can see here that link ratios in the last 7 calendar periods have been much higher than those seen in the past. This is strongly telling us that something happened 7 or so years ago that we need to understand and allow for in our modelling. Either this should be a trend which the claims and underwriting team have told us about, or one which we should be informing them about. Let's go back to our triangle link ratios and make some selections for this class. Let's say we've discussed with the claims and underwriting team, and we've concluded that this business is markedly changed in the last 7 years. One option for us could be to model this class in 2 parts, one considering data from the most recent 7 years, and the other only considering data prior to that point. So essentially I've divided this segment into 2. Another option would have been to change our segmentation to fully split the segment into 2. For now, let's focus on the recent segment, covering data from 2002 onwards. So I can exclude all of these historical link ratios, or I could just take the volume weighted average of the last 7 link ratios. You can see now I have values of 1.03, 1.28, 1.2, etc. for the selected link ratios, using the volume all average. One thing we should do at this point is check for any individual outlying link ratios which are not representative of the future and exclude them from the model. The easiest way to spot this is to look at a chart of individual link ratios. We did this earlier in the example, and now we can see that this chart looks a lot better than before, as we've excluded the older, unrepresentative link ratios. We now see broad consistency in link ratios by development period, as well as a nice trend down towards 1. What we're looking for now are any link ratios which really stand out from the pack. However, one thing I would caution against is just excluding link ratios, as they're a little out of line. One thing to be aware of is that it's probably futile trying to remove individual link ratios in the earliest few development periods. We know these early link ratios will be more noisy, and we know link ratios are skewed, so just ignore those link ratio deviations. I'd say that about 95% of the chain ladder models I run have no link ratios removed at all, although things could be a little different in longer tail classes. But as a rule of thumb, try to leave all the data in. I will give you a free pass though, in one situation. You often get a very high link ratio followed by an offsetting, very low link ratio, and this can represent an error in the underlying data. And it's natural to want to exclude that, or perhaps even better to correct the source data. In general though, we need to consider our link ratios as a precious resource. We rarely have a surfeit of them, and so need to keep as many as possible in our model. I do appreciate that I've just removed a load of old data from this model, but that was to overcome a major change in the policy lifecycle that had to be allowed for, or our model would not have been reliable. It is a very extreme example. Don't take that as a normal bit of practice. What I am concerned about though is the death by 1,000 cuts issue, where lots of seemingly innocuous link ratios are removed just because they're a tiny bit out of line. This takes up a lot of our scarce modelling time, wastes a lot of our precious data, and can unduly smooth through interesting features in our data, which actually needed to be examined and understood. Further to their preciousness, the link ratios are distributed log normally rather than normally, which gives a mathematical reason not to overly exclude them, as follows. This chart shows a frequency plot of the residuals of our link ratios, on the assumption that our original link ratios were distributed normally. We can see that everything is nicely distributed around 0, and we get a mean, a median and a mode all equal to 0. So in this scenario, if we took out a high and a low link ratio, then we retain our mean of 0. However, in the insurance world, things are not so simple. This chart shows a more realistic frequency plot of the residuals of our link ratios when we're looking at insurance claims data. We can see that most of the link ratios are still near our unchanged mean of 0, but there are some extremely high link ratios, and we can also see that we have more link ratios below the mean than above it. It's a classic log normal shape, and you get this as things can generally only get a little bit better in insurance, whereas the downsides, as we all know, can be huge, with exceptionally large claims possible on single policies. So we shouldn't be surprised if we see the odd high link ratio in our historical data. This is natural and representative of the future, hence we should keep it in. The skewness of the distribution leads to our mean, which is still 0, being higher than our median residual, -1 in this example. So when we think we're being fair by taking out the odd high and the odd low link ratio, not a pair caused or connected by an error, then we'll end up biasing our model towards the median value. And since we know the median is lower than the true mean, we'll end up with a biased low model. So we don't want to take out link ratios unnecessarily. It's wasteful of our precious resource and will likely bias our model results. The first example dataset I've been talking through was a bit special to enable me to best show off some of the checks I use. However, it's much more normal to have fairly well behaved data like what I'm showing in this new example. So here I can safely include all the link ratios in the model, noting that I'm letting ride a few funky link ratios in the first development period, and I just need to decide what average to select to apply to future development. So how do I go about selecting between volume 1, 2, 3, all, etc.? Well, firstly, I would say that almost always I would just pick one average for all development periods. Personally, I think that it looks suspicious if you don't. You can nickel and dime to get the right number, but it's a waste of valuable modelling time and makes things so much harder to explain and to justify, as well as to repeat when you come to model this segment again next time. The policy life cycle is always in a state of flux, and so generally volume all is going to give too much credit to old world conditions. Volume 1 is just too volatile to rely on. So normally somewhere between volume 2 and volume 5 is the sweet spot, which has enough data to be reliable and yet still be representative of current and future world conditions. Considering the chart of link ratio averages can help you here, as you can see when the link ratios from the various averages align. Often volume 1 and 2 are quite volatile, but you see things settling down in the volume 3 to 5 range, before being different again in volume all, due to distortion from the old world historical link ratios. Your preparatory work will guide you here. Is this a class that is changing, which might push you to a shorter average of recent link ratios? We know that there will be volatility around the true underlying development pattern in the actual data, so we need to include enough link ratios to reduce those distortions. And remember, if you're modelling on a quarterly origin period basis, then you need to look at volume 4, volume 8, volume 12, etc. Volume 1 on a quarterly basis would be extremely volatile. Also, do watch out for seasonality if modelling quarterly or monthly, although normally this changes the absolute level of claims rather than the development of them, which is natural as all claims regardless of month or quarter just go into the policy life cycle system and get treated the same as claims from other months or quarters. Before I stop, let me just give you an example of what I would consider bad modelling, where the various pitfalls I've mentioned in this video all show up. I do see things like this from time to time as a reviewer, and immediately I get flashing red warning lights that something has gone awry. Maybe the modeller felt under pressure to deliver a certain result, or they just got carried away. Whatever happened, it's very likely that a simple, elegantly calibrated model would be more robust and reliable in the long run than such an overly fitted model. So what's wrong here? Well, for a start we've got fairly random link ratio exclusions, including fussing over early link ratios that really aren't relevant to our modelling. We've got exclusion of random link ratios that are just a little high, and in some cases not even the highest link ratio in the development period. So very hard to justify and explain why we've done that. We've got what I call patchwork quilt average selection, where we jump about averages from one development period to the next with no apparent consistency. It just looks like the modeller has thought too much about the results and not enough about the underlying process they are trying to model. Trends don't change like that in reality. They emerge over time and stick. They don't flash in and out of existence. So if you finish your calibration and see something like this staring back at you, then think again, is this really the model which reflects all the preparatory work you've done and all the checking? Is it something you can explain and justify? Something which you would happily stick with for the next review and the one after that? I suspect not. So save it down and then do another model, thinking about simplicity and consistency. You'll be surprised to see how close the results are between the two models and how much quicker you built the simple model than the overly fitted one. So hopefully this video has given you a good insight into how I would perform final checks on my data and then selecting ratios to use to predict future development in my chain ladder models. In the next video in this series, I'm going to talk you through how I would smooth through unreliable link ratios in later development periods and how I go about deciding if I need a tail factor and also selecting how long that tail factor should be. You should be able to see the next video in the series on the left hand side here, so please click to move on to it now. As usual, please also like and subscribe to support these videos. Again, you should be able to see a small circle here which you can click to subscribe. And do let me know your comments and feedback on these videos in the comments section below. Thank you.